Have you ever stopped and wondered what it really takes to run a service for, over a billion people? It's not just about throwing more servers at the problem. Nope, it's about these fundamental engineering choices that were made years and years ago. Today, we're going to dive into one of the most legendary scaling stories in tech, how Facebook took a pretty simple open-source tool, Memcached, and somehow turned it into the literal backbone of a global empire. And just to give you a sense of the insane scale we're talking about, at its peak, Facebook's caching system, which was all built around this one humble tool, was handling nearly 5 billion requests per second. I mean, that's a number so huge it almost breaks your brain trying to imagine it.
So yeah, the big question is, how is that even possible? How do you get from just one server to handling trillions of items a day? Okay, let's get into it. This whole incredible journey starts with a really common problem and a foundational architectural pattern.
Right, so in the beginning, it all started with a simple but absolutely crippling problem. Their databases were getting crushed, just hammered. Every single page load, every like, every comment was hitting the database, and it just couldn't keep up. The answer wasn't a bigger database, it was to figure out a way to avoid talking to it in the first place.
So what they did was implement something called a demand-filled look-aside cache. And the logic? It's beautifully simple. First, the app asks the cache for some data. If the cache has it, that's a cache hit, boom, it's returned instantly, super fast. But if not, that's a cache miss. The application then goes to the real source of truth, the database, grabs the data, and then, this is the crucial part, it puts that data into the cache so it's ready for the next time someone asks for it. And this right here shows the whole flow perfectly. On the left, you've got that read-miss path we just talked about. You check the cache, you miss, you go to the database, and then you fill the cache. But look at the right side, the write path. This is just as important. When data changes, they don't update the cache. What they do is update the database first, and then they just delete the old item from the cache. So why do that?
Well, it all comes down to data consistency. See, if you try to update the cache directly, you can run into all sorts of nasty race conditions. Imagine 2 updates arrive out of order, you could end up with old, stale data permanently stuck in your cache. Yikes. Deleting, though, is what we call idempotent. It doesn't matter if you tell the cache to delete an item once or 100 times, the end result is the same, it's gone. And that means the next time someone asks for that data, it's a guaranteed miss, which forces a fresh fetch from the database. Simple, but so effective.
Okay, so that handles the basic logic. But this simple pattern pretty quickly ran into a whole new set of problems when they tried to deploy it across thousands of servers inside a single, massive data center. And this is where things get really interesting.
Get this, an average Facebook page load wasn't just fetching one piece of data. It required fetching, on average, 521 distinct little items from the cache. I mean, the social graph is so interconnected, right? So rendering just a single page meant stitching together hundreds of these tiny pieces of information. And this high fan-out, as they called it, created an absolute nightmare scenario. You had thousands of web servers, and each one needed to talk to hundreds of different cache servers all at the same time just to render pages. It was this all-to-all communication storm that led to massive network congestion and bottlenecks. A single slow cache server could end up delaying responses for tons of users. So to fight this, they made a really clever trade-off at the network level. For read requests, the GET operations, they used UDP. It's super fast, it's connectionless, has almost no overhead. And if a UDP packet gets dropped, no big deal. The client just treats it like a cache miss and moves on. But for writes and deletes, where reliability is absolutely critical, they used the much more robust TCP to guarantee the change actually went through. It's the best of both worlds, speed for reads, safety for writes.
But this created another potential disaster. So imagine a celebrity's profile gets updated. The cache entry for it gets deleted. What do you think happens in the next microsecond when thousands of web servers all try to load that profile? They all get a cache miss, and they all decide to hammer the database at the exact same time. That is called the thundering herd.
Their solution was so elegant. They called it a lease. When a server gets a cache miss for a really popular item, the cache server gives it this special temporary token, a lease. You can think of it like an authorization slip that says you, and only you, are allowed to go to the database to get this data. For the next 10 seconds, any other server that asks for that same item is just told, hey, someone's already on it. Just wait and try again in a moment. This super simple mechanism prevents 1,000 servers from stampeding the database all at once. Genius.
And they didn't stop there. They developed a whole suite of other solutions just for this intercluster scaling problem.
They had gutter pools of standby servers ready to just absorb the load if a cache server died, which prevented this chain reaction of failures. They partitioned memory into different pools for hot and cold data to improve efficiency, and they even built flow control right into the client to stop it from overwhelming the network. So they basically solved the scaling problem inside one data center. But now, how do you take that solution and make it work across the entire planet? Well, this introduced a whole new dimension of complexity. How do you keep data consistent across continents? So the architecture evolved into this regional master-slave model. You've got one master data center that holds the primary source of truth for the databases, and that data was then replicated out to multiple slave regions all around the world to be closer to users. But here's the brand new challenge this creates. How do you make sure a delete that happens in the master region gets reflected in a slave region thousands of miles away before a user there reads the old stale data? This massive problem was solved by what they called the invalidation pipeline. It started out as a system called Mcrouter, which basically just watched the database logs and sent out delete messages. This then evolved into a much more robust system called Wormhole, a giant pub subnetwork. Think of it like a global broadcast system for data changes, making sure those invalidation messages were never ever lost. And for writes that happen in a non-master region, they use this clever trick called remote markers to temporarily force any reads for that specific user back to the master region, guaranteeing they see the data they just wrote. Now, we have to talk about the unsung hero that makes all of this magic possible. How do you possibly manage routing requests across thousands of servers, dozens of different clusters, and multiple continents, all while handling failures and complex logic? The answer is a piece of software called Mcrouter. Mcrouter is this incredibly intelligent proxy that sits between the web servers and the cache servers. And, don't just take my word for it. As the source material says, it's not some minor utility. It is a core component that handles the full fire hose of nearly 5 billion requests per second. It is quite literally the brain of the entire operation.
Mcrouter's real power comes from its amazing flexibility. Its logic is built from these little composable modules called route handles. So, need to send a delete to every single replica to guarantee consistency? Boom, you use the all-sync route. Need to try a list of servers one by one until one of them responds for high availability? That's what the failover route is for. Need the absolute lowest latency possible? Well, the all-fastest route sends the request everywhere and just returns the very first response it gets back. This mix and match approach is just genius.
And it does so much more. It pools connections to save memory. It automatically routes around failures. It lets you make configuration changes on the fly with zero downtime. And maybe most importantly, it keeps the web servers and the cache servers themselves incredibly simple and fast by just taking on all that complex routing logic itself.
So, after this incredible journey from a single server to this global behemoth, what are the big takeaways? What are the core philosophies that actually made this all possible in the first place?
Okay, first, separating the cache from the database was absolutely key. It meant they could scale each one independently based on its own specific needs. Second, that smart client simple server philosophy, perfectly embodied by Mcrouter, was critical. It kept the core component, Memcached, lean, mean, and fast. Third, they learned to embrace eventual consistency. They understood that for a lot of things, being available and fast was more important than being perfectly consistent every single millisecond. And finally, they knew that operations are paramount. Building a system that you can actually monitor, debug, and safely upgrade is just as important as the initial design.
Now, of course, the story did evolve over time. For the core social graph, Facebook eventually built a more specialized system called Tau. But that doesn't diminish the legacy here at all. The principles they pioneered while scaling Memcache, the intelligent proxy, least space concurrency, robust invalidation, they became the bedrock of modern distributed systems design.
At the end of the day, what this all means is this. These aren't just Facebook's problems. These patterns of separating concerns, of using smart proxies, of trading a little consistency for a lot of availability, they are everywhere now. So the next time you're using some massive online service, just think about the invisible architecture humbling away underneath it all. What modern systems that you use every single day do you think are built on these same hyperscale principles?